layer neurons and 2 output neurons. Okay, so 2 hidden layer neurons and 2 output neurons. So suppose our system looks like this. Okay. So sigma Okay, and again, let's pick the same example so we can easily relate to it. 2 inputs, x1, x2. So obviously they will go to this one, this one, this one, this one, S, A, S, A, right? Then this will go over here, this one will go over here. This one will go over here, this one will go over here. Okay, so again we are doing a classification 2-class problem. So now the way it will work is if the output over here is close to 0 and this is close to 1, that means it belongs to class X. Okay. If it's the other way around, if this is close to 1, this is close to 0, then it will be class O. So we are still doing the same 2-class classification problem, but instead of using a single neuron on the output, for whatever reason we put 2 neurons. Okay. Reason I'm putting 2 is not because this is a better approach, but just to show you how the gradients will be computed in this particular case, right? Okay, so let's use the same terminology as before. This will be W11, this will be W12, W21, W22, right? This one will be again W11, input 1, and this will be W12, this 21, W22. And S and the A. Okay. For the biases, let's call this B1, B2. So remember here we'll put superscript 1, superscript 1, 1, 1, 1. Let me call this S1A1, S1A1. Sorry, S2. Okay, so the superscript over here will be 1, superscript will be 1, because it's layer 1, right? Okay, very similarly over here we'll use the 2, 2, 2, 2, 1, oh sorry, 2. Okay, B1, B2, S1, S2, 2, 2, 2, A1, A2, 2, 2. So this will be our architecture, right? Okay, so as you can see previously we had 9 parameters. So now how many parameters will there be? 6 in each layer, 4 weights and 2 biases. So total will be 12 parameters. Okay. So let's pick one example and see how the gradient will be computed. Okay, so now it becomes a little more complex. Okay, the reason it becomes more complex is, let me sidetrack first and show you, in general, if let's say here's A, some B, B branches to C, branches to B, right? Then basically E, F over here. So here's one output, here's another output. Okay. So let's pretend over here is the x input, and we are interested in some kind of a loss function over w is our goal. So the gradient of this weight with respect to the loss. Okay, so these are our outputs, right? So there's some kind of a loss involved over here. Okay, but the loss is now dependent on both outputs, not just one output. Okay, so this is where we need to sum the gradients. Okay, so the way it works is there's a path over here, and there's a path over here before we get to the, there are two paths involved. Okay, so over here, it will be basically, let me put it in black because that's easier to read. So this will be sum of two gradients over here. Okay, then once we add the two gradients, then it's, step by step, it's same as before. Okay, so let me pick an example first. So I'll do a couple of examples for you over here. So let's take a look at, for example, partial L over partial W11 of 2. Okay, and we'll also now try to develop a little bit more intuition rather than just simply brute forcefully writing all these gradients, so that just by looking at it, you can tell me this is what the gradients will be, right? Okay, so as you can see, this will be partial L with respect to so again, draw the path. So the path is over here, right? Okay, so partial L over partial W11 of 2. Okay, so let's take a look at the loss also. The loss, for example, could be defined as y1 minus 2 squared plus y2 minus, so let's call this y2 minus 2 squared and half, right? Okay, so as we write this, this will be partial L over partial A1 of 2, right? From here to here. Then partial A1 of 2 over partial A1 of 2. Then partial S1 of 2 divided by W11 of partial. Okay, so so now let's put in the details over here. What's partial L over partial A1 of 2? Take a look at this expression.
y1 minus A1.
See, with respect to A1, this part is 0. This is just a constant, right? So it will still be what?
Minus of y1 minus A1 of 2.
Okay. Then let's go to A1 of 2. Again, if we assume the linear activation function for right now. 1. Then lastly,
A1.
what is the expression for S1 of 2? S1 of 2, as you can see, is A1 of 1 times W1 of 2 plus A2 of 1. W1 2 of 2 plus B1 of 2. Right? Everybody agrees? So A1 gets multiplied over here, this A2 1 gets multiplied by this W1 2. Okay, so what is the partial with respect to W1 1 of 2?
A1 of 1.
Okay, so now, like I said, let's try to develop a little bit of intuition over here. Okay, so one way to think about this will be anytime we go from here to here, right? We're taking a look at this function. Depending upon this function, it's the derivative of this function, right? If it is a linear function like this, then what's the derivative over here?
1.
1. as we go from here to here, essentially, as you can see from here, what it's doing is, it's essentially, if this is the path we are following, it's taking a look at the previous output. Okay, so the previous output is A1 of 1, so that's why this will show up. Now, without going through any of this, let me see if you can tell me what will be the W12 gradient.
Minus of y1 minus a1 of 3
So that stays the same.
into 1
Okay, and what's the previous output?
into a2 of 1.
A2 of 1. And you can verify it yourself, by going through the detail and seeing. So the derivative with respect to the weights is always the previous output. If it is A1 over 1, if this was like a single layer network and I wanted to take the derivative with respect to this, then what will be the derivative? What's the previous to it? X1. So then it will come out to be X1. Okay, so that's one point. Okay, then I'll show you another important point in a second. Now let's go to, for example, let's try to figure out what's the gradient with respect to W1 of 1. Okay, so the gradient with respect to W1 of 1 will be. Okay, so now, like I said, we have to accumulate two paths over here. A single path will not work. What are the two paths over here? One will go from this dotted line over here. What's the other path over here? So these two green paths have to be accumulated, then added together. Okay, let's take a look at the top green path over here. So that's easy. Up to this point, we already created, right? Or let me, for the completeness sake, let me write it partial W11 of 2. Sorry. Partial L over partial A1 of 2. Then partial A1 over 2 over partial S1 over 2, like here to here, right? So I'm going to the top path now. So partial S1 over 2 over
W1
the previous output.
a1 of 1
Partial A1 of 1, then partial A1 of 1 into
S1 of
1, and then partial S1 of 1 over partial W1 of 1.
plus slope of
Right? Okay, so what is this over here?
minus y1 minus a1 of 2 into 1.
Oh, I forgot. Okay, I haven't added the second path yet.
Second part.
Let me also put a plus sign and do the second path also. Now let's go to the second path. Second path will be partial L over
a2 of
A2 of 2, partial A2 of 2 over
S2
S2 of 2 times.
partial S2 of 2.
The previous one is A2. Sorry, I'm going up. I'm going up. So it will be
a1 of 1
partial S2 of 2 over A1 of 1 times partial A1 of 1 over partial S1 of 1 times partial S1 of 1 over partial W1. Okay, so after the plus sign, that's the bottom path. To the left of this plus sign is the top path. Okay, so this is one way of doing it, right? But are we repeating a few things over here if you take a look?
Yes.
See this part, A1, S1, S1 to W11, meaning this part is the same as over here. Do you agree?
Yes.
So can I
Common.
take it common and add the two? Okay, so if I did that, then what will this become? This will become like this. You guys agree? So basically, essentially, if you take a look at the picture, what I'm doing is I'm adding these gradients, right? And then multiplying it with the common path. So that's what we did. So let's try to write this one now. So what will this be? Partial L W1 of 1. Okay. Let's take a look over here. This.
Y1 minus A1 of 1. A1 of 2, sorry. Into 1.
Okay, so this is this one. That's 1. Then this one.
Output of previous, that is A1 of 1.
Okay, see where did I write S1 of 2? If I do the derivative with respect to A1 of 1, what do I get?
W11 of 2.
W11 of 2. So the weight that connects these two, once we take the derivative with respect to the previous output, the derivative becomes the weight that is connecting the two, right? Okay, so that part is done. Now let's go to this part. So this will be
Y2 minus A1.
C minus Y2 minus 2.
Into 1.
This part is 1. And S2 of 2 over A1 of 2.
W21 of 2.
So what's the weight that's connecting?
W21.
W12 of 2. See, that's what leads me to A1 of 1, right? So this will be W12 of 2. Right? Then let's go to the last part. Last part is easy. This part, what's that? 1.
1 into
And then
X1.
what's the previous to this one is x1. So, or you can write the expression for the S1 and see that will be, sorry, that will be x1. Okay, so so that's how now you can, go home and practice. I mean, not now, we still have more lecture. You can compute the W12, W21, W22. So as an example, let's go to W21. What will be summed over here? If you take a look at this, right, where's this feeding from? One possibility will be from here to here. Then another possibility will be from here to here. Will we also go from here to here? No. So just checking. Okay, so this one, so two paths, right? So one will be this path. Okay, one will be this path over here. Okay, so now let me give you a more intuition into it so that even if we have a more complex system, just by looking at it, you can right away write the gradients. You don't even have to go through all these partials that we were writing, okay? So, so we'll define a term called delta. Okay, so the way we will define a delta is, so think of a delta as the computation in the middle of the neuron. Okay, so visually think of it this way. If this is sigma, this is the activation function. Remember, if there's a loss involved or if there's another neuron over here, we'll do the derivative, then we'll do partial A over partial S further to come to the gradient up to this point. So this delta will exist, whatever that is. Okay, for example, for a single neuron system, let's go to a single neuron system very briefly. Okay, A, S. Suppose we're doing regression, so we can make it easy, X and W. Okay, here's the loss. Okay, so remember the normal way of writing this will be partial L over partial W equal to partial L over partial A over partial S over partial W, right? So, like I said, delta is up to this point in the middle of the neuron. So, what is that part over here?
First level.
So this is what we would suffer delta. Okay. So if we compute the deltas, then what you will see is, let's say we have a 2-neuron system. I mean many layers, but just 2 neurons. So let me see if you can understand this. Then I'll give you a break and we'll come back and further strengthen it. So if you take a look at this part over here, right? Okay, suppose W21 feeds over here. Suppose W11 feeds over here, right? Okay. So let's focus on, okay. So can we compute the delta over here?
Yes.
And let's pretend these are the outputs, right? So from the loss function, like I said, you did the multiplication, derivative of the loss, derivative of the activation, whatever that came out, let's call it delta 1. Same way, derivative of the loss, derivative of the activation, whatever that product came out, suppose we call it delta 2. Okay, so remember then, as I said, we sum the gradients over here before we go further. Okay, so then what we'll do is we'll compute the delta over here. So the delta over here, what you will see, very interesting behavior is, and you can verify by expanding these equations, is that this delta in this neuron in the middle will come out to be W11 times delta 1, whatever weight feeds it to it, plus whatever weight feeds to this times delta 2. Okay, once we know the delta, then let's say we are going over here, X is the input, W. So then further we have to multiply, remember, if this is S, partial S over partial W, which is always the previous output, right? So the overall partial L over partial W will turn out to be
Delta into
this delta
the
into the previous output. What's the previous output over here? X. So our theory will be, and after the break we'll go further so that you is start out by computing the delta over here, Then based on these two deltas, can we do the delta over here? Because whatever the weights are, that will give us the delta. Can we do the deltas over here? Then from these deltas, can we compute the gradients?
yes.
Yeah, based on the previous output. So it will be a piece of cake. No need to remember all these partial derivatives, but those deltas again don't come out of out of the blue. They are basically a shortcut to all of these. If you expanded those deltas, you'll come up with exactly what we discussed over here. Okay, let's take a break and we'll continue.